Hey, how are you?
Good afternoon. Thank you for coming out this afternoon. This is the John and Donna Hall Engineering Lecture Series. We are blessed to have this series through the generosity of Jim Gray, a great friend of John and Donna Hall, who endowed this series on their behalf. Today we're very fortunate to have with us Dr. Michelle Buchanan from the Oak Ridge National Laboratory. Michelle joined Oak Ridge in 1978 after earning her undergraduate degree in chemistry at the University of Kansas. I assume you were cheering loudly this last week.
Yep.
And a PhD in analytical chemistry from the University of Wisconsin. She is currently Associate Laboratory Director for Physical Science at Oak Ridge and oversees 4 Oak Ridge divisions: Chemical Sciences, Metals and Ceramics, Physics, and Condensed Matter Sciences. Prior to assuming her current position, she served as Director of the Chemical Sciences Division from 2000 to 2004. She's also on the faculty of the University of Tennessee's Genome Science and Technology Program and Director of the Center for Molecular Cellular Systems, a multi-institutional program that deals with the characterization of protein complexes. She's the author or co-author of many published papers and a book on Fourier transform mass spectrometry. And as you might imagine, she has many professional interests. She's currently a counselor for the Division of Analytical Chemistry of the American Chemical Society. She was North American Editor of Biological Mass Spectrometry and has served on the editorial boards of Analytical Chemistry, Organic Mass Spectrometry, the Journal of Mass Spectrometry, and Biological and Environmental Mass Spectrometry. She currently serves on a number of advisory boards. I won't name them all, but she serves on the advisory board for the biotechnology at Sandia National Laboratory, and she serves on the committee of visitors for the School of Engineering here at Vanderbilt. Michelle, thank you for being here.
Thank you. I'm delighted to be here, and I really appreciate the invitation to come and speak on a topic that's very dear to my heart. I'll warn you that this is a pretty high-level lecture. It's not getting down into the details of the science, but it's kind of an overview of where I think energy is right now and the type of opportunities there are for science and engineering to make a real impact on this nation and the globe's future in energy. And so I'll start out telling you a little bit about the state of energy across the globe, and more about specifically some workshops that have been run through the Department of Energy, Office of Basic Energy Sciences, that really focused in on the basic research opportunities that we see that are out there for energy research. And yes, I did root for the Jayhawks last week. This exact time last week, I was in Chapel Hill. Okay, and so this was like 2 days before Kansas had to play Chapel Hill, and I didn't say anything, but my host says, "This lady is a Jayhawk," and everybody goes, "Woo!" You know, it was awful. It was awful. So this is a much friendlier audience to start with. I don't know how it'll be at the end, but that's okay. I started giving this talk about 5 years ago, and when I gave this talk 5 years ago, people would look at me and go, "Oh yeah, energy, it's important and everything." Well, this is a much easier talk to give these days, okay? And I've updated over the last 5 years, but everybody is aware of the fact of the need for energy. And the fact is that we see it every day. I love this. This is about 3 years old. That was the last time gasoline hit $3. That was up on the web. And we know that energy demand is going up. We know that there's limited supplies of fossil fuels. We know about energy security concerns and also environmental and climate concerns. If you look at this in total, I don't think there's ever been a time when the public should be, if they're not already aware, of the inextricably linked issues of energy, the economy, security, and the environment. These go hand in hand, and it's something that we have to think of as we go forward to see Where's our economy going to go? Where is our jobs going to come from? Where are the technologies going to be needed? These are things that we need to, as a scientific community, we need to start thinking about this and contributing to the solutions. This is too bright to see, but let me just tell you, this is a simulated night sky, okay? And this is kind of a pasted together pictures from outer space of the globe. And if you could look here, you can see, probably even with the lights on, all the lights in North America, especially along the eastern seaboard. If you look across into Europe over here, Africa's down here, it's pretty dark. You see India and China over here. This is Japan out here in the ocean. This picture was pieced together in 2000, okay? If you were to take that picture now, you would see a lot more lights in the continent of Asia, in China, and in the subcontinent of India. And we know that the demand for electricity is growing by leaps and bounds in these countries whose economies are emerging. These countries need energy, they want energy, and it's something that we have to be thinking about. We see that the U.S. has only 4.6% of the world's population, yet it only produces about 17% of the energy, but we use about a quarter of the world's energy, okay? This equation isn't going to last much longer. And of all the world's energy, there's about 400 quads, that's quadrillion BTU, that's an unusual unit, but as the engineers know, you guys use BTUs, so you can relate to that. But we use about 98 quads of the 400 some quads that are used globally. And this is a real problem when you see this. Two things, you can see how some countries have a lot of electricity. I see up here, it looks like this little thing's an island. Actually, that's South Korea. North Korea is dark, okay. The continent of Africa is pretty dark. Even Australia is pretty dark, okay? So it's kind of an interesting look at where the energy use is. The other thing is looking from outer space to see how much energy is wasted. You know, it boggled my mind when I saw that. I mean, this is all light that's coming up out of the Earth, and we waste a lot of energy, okay, just in incidental lighting at night. This is just a reminder of how we got to where we were. If you look at the time when the Europeans came to the United States, okay, to the North America continent, up until, you know, just maybe about 150 years ago, the economy was all run on wood, okay, just burning wood for energy. There wasn't much need for energy other than for heat and light at night. But then we started going through the introduction of new machinery to do work for us. Wood was initially the fuel of choice, and then we ran into use of coal and petroleum as we got into electricity and combustion engines. And you can see now that if you look at the quadrillion of BTU now that we use, you can see that predominantly the use is in petroleum. We have some natural gas and coal, all fossil energies, a little bit of nuclear power. It's been fairly stagnant over the last 25 years or so, and renewable energy. Okay, so that's kind of what our portfolio looks like. And then you have to repeat this for every country as to what their distribution is around the world. This is a nice plot that I like a lot. This one actually shows that you look at the GDP, okay, this is the per capita for each person, okay, in thousands of dollars versus energy consumption. And you can see that the countries that have a poor economy use less energy, and those that have a better economy use more energy. And of course, there we are up there. Here's China. This was from 2000, and you can see that China's going to be moving up here in this area because their increase of energy. In fact, I was telling somebody today that China has the most reserves of coal of any country in the world, okay? They are using coal so fast that they can't dig it out of the ground fast enough. They're actually a net importer of coal now. It's just amazing how much energy is being used. And those of you who've gone to China know that the consequence of burning coal is that their pollution is just unbelievable. Unbelievable pollution. And so this is increasing day by day as more people want cars, more people want HVAC, they want electricity to read at night. So this is going to happen as more and more countries become more affluent and want to have the same sort of standards of living that we've been enjoying. So today in the United States, how is our energy distributed? We have, for example, again, this is the 100 quads. 100 quads is equal to about 3.3 terawatts. Predominantly, our energy is coming from fossil energy. It's coming from oil, gas, and coal. About 10% for nuclear and about less than 10% for renewable. And I don't know how many windmills you guys have around in this neck of the woods, but in Oak Ridge, up on one of our mountains, they've been putting these huge windmills. I mean, they're just gigantic. You can see them from miles away. So this is, obviously, this portfolio is skewed to the where we are now, but we've got to change that distribution for the future if we're going to remain with plentiful, cheap, and abundant and secure supplies of energy. I think what's interesting when you look at, that we use all of these hydrocarbons to make electricity as well as using it for transportation. A lot of it's going to transportation, that we're just burning it, it's going up, CO2 is going up the tailpipe for houses and for industry. But when you look at the net use, I think one of the interesting pieces of data that came across was that 62% of our energy is wasted, okay? And I look at that as a challenge for us as scientists and engineers on how to best use energy, because if we're losing that much, that's one place where we could actually go save a lot right now. I heard Nate Lewis give a talk on Monday, and his quote was even more interesting, is that 80% of power is lost going from coal-fired electrical plants to an incandescent light bulb. And that's a lot, okay? And you start thinking about the heat and IR losses across the lines. I mean, it makes sense. So again, we've got to have a better way of utilizing our energy. That would be a big step forward, okay? So I think energy conservation, better use of waste energy, I think of all the technologies for thermal electrics and other sorts of waste heat recovery would be very useful. But the bottom line is that even with all that, that's still going to be inadequate to meet the needs of the future. And another piece of data somebody told me is that, it used to be when we had a cell phone, it had a little tiny battery in it. And every time you turn around, they're putting new things on cell phones. So you have cameras, you've got, iPods in there. My BlackBerry now has a GPS in it, so everything's on one thing, And so they had to put more and more energy into these things. So everything we need is taking more energy. It's just becoming things that we didn't have 20 years ago are using energy in our houses, in our offices. This is another slide that I'm sure you've seen many times, and this just goes to show you the relative tracking of the CO2 with global mean temperature. And of course, our native son, the Vice President, made this very evident this year, and I think more and more people have, this used to be a hard slide to show, and have people think that there was some correlation, and in some areas it's very controversial still, but I think that we know that we are getting global warming, and that part of that is from human-made sources, so this is something else that we need to track. So the bottom line is in this energy issue is that it's hitting us hard now, it's hitting us in the pocketbook. It's causing people to think about where they work, where they live, because it's getting to be so expensive to commute back and forth to work. How do we get out of this conundrum that we're in right now? Well, one of the things is, as I mentioned, is better energy efficiency. There's quite a bit of interest and excitement about biomass, making ethanol out of corn or grass clippings or wood chips or those sorts of things. Big interest in carbon sequestration to pull the CO2 out of the atmosphere and put it underground, or catalyze it to make other sorts of hydrocarbon type materials is another area of research. But in the long term, we really can't deal with carbon very much. It's going to be a problem. We're going to run out of carbon. And again, I was telling a story today that a guy that was at a conference back a few years ago was from ExxonMobil, and we were talking about energy issues and everything. And he said, I'm from the oil company, and I'll tell you that in 50 years, if we're still burning carbons for cars, we're in trouble, because I want those carbons for chemical feedstocks. Your way of living, just think what would happen if you didn't have plastic, and it's just infinite, the water bottles, the desktops, diapers, plastic bags. We need carbon sources that are not going to be petroleum for very long because it's going to be very expensive. And a lot of the industry is going into biomass and trying to research how to take those carbon sources into plastics and other sorts of materials. So in the long term, 50 years, 100 years out, we would really like to be in a carbon-free energy system. It's not going to be 100%, but I think this is something that people are really thinking about, looking at renewable energy, whether it's solar, whether it's wind, different types of energy sources, next generation nuclear, and then looking at recoverable energy as a way of looking at how all the pieces are kind of sewn together. So this is a slide from Nate Lewis, and if you guys have heard Nate Lewis's thesis is that it's either solar or nothing. Okay, so I'm not quite that dogmatic about things, but I'll just show you this because it does show you where the energy is coming from renewable sources. It doesn't include nuclear, but if you look at renewable sources, these are numbers that he came up with, and the fact is that wind, there's only about 2 to 4 terawatts that's extractable right now, effectively. Tide and ocean currents, about 2 terawatts. Hydroelectric, we've pretty much tapped into. You know, there's not very many other places where we can have hydroelectric power sources. Geothermal, again, there's there, but only a small fraction is recoverable. Biomass, he shows these numbers as far as what can be used for arable land that's not used for food. And his point is that solar is the big winner in this thing, that we have so much energy hitting this earth every day that it can supply all the energy. Now, my argument, you know, if he was here, we'd have this argument, but the fact is that solar isn't going to work in the Upper Peninsula of Michigan. If anybody here from Houghton, the sun doesn't shine on Houghton very much, but it will shine in certain places. And I think that we have to look at a portfolio of energy. It's just not solar. Solar isn't going to be the answer. We're going to have to use different types of energy depending on where we live, okay? And you see that now. I mean, the Europeans are kind of doing different things than the people in Brazil who are making ethanol because they got lots of land and everything else. But the people in Europe are looking at solar, they're looking at hydrogen, they're looking at geothermal. And I think every locality around the globe is going to look at what best suits them. So that's my take-home message from this particular slide. But I think this is an important slide, and I love this slide. We can't get from here to there to use any of those energy sources unless we make big changes. And the big changes is that we're not going to be able just to tweak today's solar cell to make a much higher efficient solar cell, or tweak today's fuel cell to make a much more efficient fuel cell. That we really can't think about incremental improvements. And I like this slide because this just shows you that the candle didn't get its origins. I mean, it was not derived to make this light bulb. And so we have to come up with new concepts, we have to come up with new technologies, and the only way that we're going to come up with this is to do research, okay? And this is a big theme that a lot of people believe, is we need to invest in research in this country to look at basic research and engineering so that we can get to where we need to be in the future. So that's what this bottom thing says, that you can't see very well in this particular light. So we really need to invest in these technologies, and the sooner we invest in it, the better off we'll be, okay? And another point that I'll make is that Millie Dresselhaus, and I don't know how many of you guys know that name, she has been very active in the energy forum, and she was sent by the State Department to Europe to be the United States representative at kind of a G7 meeting of people from Europe and Asia to talk about the global energy crisis that we have right now. And she came back and she said she's literally frightened because the Europeans and the Asians are putting so much research and infrastructure into solving their energy issues that we're very far behind. And she's literally concerned that we may not be able to keep up, and eventually we may have to get those technologies from other countries, which would not be healthy for our economy. So this is something that happened about 5 years ago. This got started. The Office of Science started thinking about what they could do to contribute to advances in basic energy research that would lead to these revolutionary changes, kind of these just really world-changing ideas that would come up with these energy technologies. And it started off with this first workshop here, which is this research needs for a secure energy future, which was kind of this holistic, very broad idea of what kind of technologies do we think are going to be worthwhile to invest in. And so from that, we got together experts in the field, people who work in industry, people who do applied research, and we said, okay, where are the bottlenecks right now? Where are the technical bottlenecks that you really need a breakthrough in order to make a highly efficient solar cell? Or where do you need to get a much better battery, okay, that can exceed the 4 volts that we have now as a limitation? And so from that came these workshops, and today I'm not going to talk about all these different workshops. I'm going to talk specifically about the hydrogen economy workshop, the solar energy workshop, electrical energy storage workshop, and then this last one just briefly, primarily because those are ones that I was heavily involved in, and they kind of fit together in many respects. So I'll just go into those in a little bit of detail. The question is what does science and engineering have now that we didn't have a few years ago that could really make a breakthrough in this area? And I think the people on these programs, on these workshops, came up that we have a lot of advances in nanoscience and analytical tools and computation that is allowing us to design materials, okay, down at the atomic and molecular level that have unique functionality, okay? We didn't have that 10 years ago. We were really working with bulk compounds, bulk materials. We were essentially, making things out of big pieces of material to make small materials. But now we can take atoms and molecules to come up with things like block copolymers that'll give you membranes for fuel cells and things like that with tailored holes. We don't have to drill the holes. We can actually engineer them into the material by design. So the idea is that with these capabilities that you can get enhanced mechanical properties, improved high temperature performance. If we could take steam generators, whether they were coal or nuclear, and take them up to the higher temperatures and pressures, we could get a lot higher efficiency out of it. But our materials fail at those higher temperatures and pressures. There's no lifetime to them. Smart materials tailored to change properties. You could think of solar cells that you could use on your roof that would change depending if it was cloudy or whatever as far as their properties are concerned. Efficient storage materials, selective catalyst, and many more examples that have been brought to bear with the types of advances we've been getting in the 3 legs, as I would say, would be nanoscience, analytical tools, and computation. So the real thing is that we have to look at advances in materials and chemistry, and they're key to meeting the energy needs. Okay, those are 2 areas that we really have to look at, and those are meant in broad terms. As I was talking to somebody today, is that chemistry is no longer just chemistry. It's biology, it's engineering, it's all these different things. The same way with materials science. They just kind of all blend together, no matter if it's organic, inorganic, biological, whatever. So looking at improved performance under extreme conditions, tailored functionality, and new paradigms, mimicking nature, looking at some of the things as I discussed with somebody this afternoon on looking at biomimetic type materials for solar conversion, materials that are self-repairing. Nature repairs itself, but we don't have materials that repair itself. There's a few examples, but we need to be able to do that so materials don't fail. And the idea is that whatever we do will have broad impact to other DOE mission needs and also for other technology needs outside energy. And the other thing that was really pointed out in these workshops is there has to be close coupling between applied and basic research. Okay, you have to have the synergy between new advances in basic research that can propel the applied research, but also the needs in applied research that can then bring more ideas to the basic research community. So these are synergistic relationships between applied and basic. Oop. Okay, so I'm going to start now and look at hydrogen. And this was when this was first brought up, and I'm kind of doing these in chronological order. When President Bush got up and said that in the year 2016, your child born today is going to be driving a hydrogen car, It was probably the worst thing that anybody ever said. I don't know who gave him that line, but that's not what they meant. But the hydrogen economy, people, you know, and I know there's a lot of engineers in this room, so anybody that knows a lick of sense about thermodynamics knows that if you're going to convert fossil fuels to hydrogen, it doesn't make a whole lot of sense. Why don't you just burn them, right? Okay, so that's not what this means. Okay, so the whole idea of the hydrogen economy is we were not going to a hydrogen economy. What this meant is, in the scientific sense, production, storage, and use. That's what they meant by economy, okay? Not that we were going to, everybody give up everything and we're going to be, you know, making making hydrogen. So when I think about this now, think about hydrogen as a means of storing energy, okay? There's no place you can drill a well on this earth to get hydrogen out, pure hydrogen, okay? You don't get it out. You have to get it from someplace. So where do you get it from? Okay, you could get it from fossil fuel reforming, and we do that. There's a lot, about 10 megatons of hydrogen made every year. Kingsport, Tennessee has a big reforming plant, and they make hydrogen to make all their polymers and things down there. So that's technology is there. But where we could get it from is from water, solar, from nuclear energy. This is really interesting. This is a way to recover waste heat from a nuclear power plant or any other sort of steam-powered plants. And bio-inspired, that's what nature does. Nature can change sunlight into fuels, including hydrogen. So if you do this, okay, one of the nice things is think about these cyclical energy sources. So you can generate solar or wind or whatever. Instead of having a battery, you can split water, store it as hydrogen, and then use that hydrogen later. So that's what we're talking about, is just using hydrogen as a good way of smoothing out the cyclical nature of solar, wind, and other sorts of technologies. And so you could use it in your car, or you could have a windmill by your house where you split water and stored the hydrogen right beside your house, and then use that to heat your house or whatever. So energy storage is important here. You can store this as a gas or a hydride. And then use of hydrogen in automotive fuel cells or in stationary electrical generation. So those are the three parts of that economy that we need to look at. And just quickly, we don't want to do fossil fuel reforming in the long run. Okay, that's not a good way to do energy. Good for the chemical community right now, but not for what we want to do. So in production, again, I mentioned this 9 million tons a year going to 150 megatons is what we need to run all of our cars and trucks if we do what the president said is to change over to hydrogen cars. And there's pluses and minuses there. And like I say, I'm not a real advocate for doing that as much as I am in storing energy. Storage is a problem for cars because you have to carry it on board. That's not the issue. It's just that to compress gas, either into compress hydrogen into a gas or into a liquid, takes energy. So you have to worry about that. So people have moved on to chemical storage or physical sorption of these materials on nanostructured materials. There's a lot of research being done in those areas to try to get these hydrogen stored more effectively and cost energy efficiently. And then fuel cells. Fuel cells right now, this is about what a fuel cell costs per kilowatt, and we need to get it down here in order to use it as a substitute for, this is as a fuel cell, not as an ICE, but as a fuel cell. So there's a lot of technical challenges there. And the workshop went into detail about the types of things that people thought really needed breakthroughs in technologies. Here's the drivers for an automotive fleet, and you guys have probably seen these commercials on television. This is a BMW 7. They show that on ESPN, I see now. This has a hydrogen tank in the back. People worry about hydrogen safety. I've never ridden in a hydrogen car, but tests have been done that shows that if your car goes up with hydrogen, it goes up, which is better than having the gasoline go down and encapsulate the car, which is what the problem is. So people claim that hydrogen might be safer. Okay, again, I'm not going to weigh in on that particular argument. But the fact is that hydrogen is still a long ways off, okay, as far as being able to do this. But the European Union has put 2.8 billion euros into hydrogen fuel cell research. Japan has doubled its fuel cell R&D to $268 billion, okay, last year. And Iceland projects it'll be on a full hydrogen-based economy by 2050. They're very serious about hydrogen, okay? And they're using, right now, they're using all means, the solar conversion, all sorts of different ways, but that's where they're planning to go. So there's a lot of activity across the globe in hydrogen research. So these were the priority research directions. So these are the very high-level areas that the core of experts, both fundamental and applied scientists and people from industry, sat down and said, these are key areas that we think are the bottlenecks that need to be broken. Okay, we really need to break through to come up with new things. Solar photoelectrochemistry and photocatalysis, to be able to harvest that energy from the sun, then use the hydrogen as a means of storing that energy when the sun's not shining, okay, so that you can power your house at night, etc. Looking at bio and bio-inspired hydrogen production, this is the Gretzel cell, which was a breakthrough. This is something that a lot of people are working on, where they actually have dye-sensitized solar cells so they can get a broader use of the solar spectrum. Again, this is to look at the redox reactions that are in the cell itself. Nuclear and solar thermal hydrogen, again, this is really a way to harness that waste heat. Okay, when you get out of a nuclear reactor, okay, that you see running up and down our lakes out here, they are actually putting a lot of energy into the water. Okay, they're removing the water energy from the reactor, and they have to use cooling water. Well, what would happen if you could take some means of capturing that energy and then using that then to split water to make hydrogen? It's a way to recover energy and store it for other uses. So there's a lot of different research needs in those particular areas, and I'm not going to go through all the different areas. Hydrogen storage is the worst thing, okay? If you're going to use it for transportation, this is a real bottleneck. But like I say, I think that there's a lot of merit to saying use that hydrogen for your house. Use a stationary hydrogen source to recover energy. So you can use tanks or gas. Those of you who are engineers out there know hydrogen. You can only compress it so far, and then that's it. So you can only get about this megajoules per kilogram for compressed hydrogen is down here. For liquid hydrogen is right there. Turns out the best hydrogen storage is our old friend gasoline up here. Okay, hydrocarbons are really good. And in fact, there's a couple companies who are looking at using hydrocarbons as a way of storing hydrogen. Okay, so I talked to a guy from Air Products, for example, one of the largest producers of hydrogen. They're looking at using hydrocarbons. So if you're going to use transportation, it is problematic. You can use it for non-transportation areas. But for transportation, it has to be lightweight, affordable. One of the things that you have to worry about, both for energy storage and for fuel cells, when you step on the accelerator, you want the car to do something, right? And so you've got to have, if you're going to use a solid type material to store energy, whether it's a nanostructured material for sorption or if you're going to use a chemical hydride type sorption, you've got to be able to get the stuff out of there very quickly. So it will take physical type things, but it might take a catalyst to try to get the material off. So you have to think about all the reactions that have to happen and whether they'll be fast enough. So these are the areas that people are looking at. Again, this was funded back a few years ago. There was a solicitation out, and there's been some really very interesting science that's been done and some real progress made as to the weight percent of hydrogen that people have been getting on some of these chemical and physical sorbents. So metal hydrides and complex metal hydrides, and then nanoscale and novel materials. You're probably familiar with, hydrogen sorption on nanotubes and other sorts of nanostructured materials, looking at these metal organic framework type molecules, looking at good old friends like sodium aluminum hydride here. This is a plug for SNS. Those of you who aren't familiar with the spallation neutron source in Oak Ridge, one of the things that is very beneficial about studying hydrogen with a neutron source is that you have the ability to see these light atoms, which you can't with X-rays very well, and so you're able to see sorption on materials using the spallation neutron source. And because of the contrast here, this is what X-rays does, is that your absorption goes up with Z. Here it's not related to Z, but you have different cross sections for different atoms, and hydrogen and deuterium have not only different cross sections, but the sign is different. So you can either see them when you look at neutrons, or you can make them with protons and you don't see them, so you can contrast that based on how you do that. So there's a lot of research being done by users who come to Oak Ridge to take advantage of neutron science to work on hydrogen storage. The fuel cells, and I know there's, somebody said the new chemie person will be a fuel cell person, which is nice. Fuel cells are very interesting. You don't have to use hydrogen for fuel cells. You can use ethanol or methanol or other sorts of materials. And they're pretty complicated devices when you get right down to it. There's a lot of chemistry and physics going on in these materials. And one of the things that you have to think about is that there's actually 3 percolation networks within these fuel cells that you have to worry about. Gas transfer, you have to worry about ion transfer, you have to worry about electron transfer, and all of these things have to go on. And so design of these membranes is very important. Being able to design these membranes to be permeable to some things, impermeable to other things, to work at different temperatures, to work very reliably is very important. And so there's a lot of work being done here and elsewhere on these membranes where they can work in lower humidity with higher durability and higher ion conductivity. Cathodes, those of you who know electrochemistry, doing electrochemistry in water, you always have the problem about overpotential and limitations of the voltage that you can put on these electrodes and things. And so this is still a problem with the fuel cell, because it kind of works like an electrolysis cell backwards. And if these are to be efficient, they have to be reliable for many, many years. These fuel cells, especially the solid oxide fuel cells, are widely used in places like Alaska and other places that don't have ready supply of electricity, and a lot of communities rely on these, and so it's very doable. It's a very doable thing, and to run a car on this will take some advances that I think these areas address. So these are the priority research directions, and I won't go through this in the sake of time. But you'll look here that one of the things we have to do is we develop new technologies for synthesizing these materials, being able to get analytical measurements that are able to identify the structure and the reactivity of these various materials at the molecular and atomic scale is very important. And we're getting those tools. We have electron microscopes and scanning probes and other sorts of technologies that will allow us to do that. And then theory modeling and simulation is very important, that it's closely coupled with our experimental programs, whether it's the synthesis or in the characterization. I think when you go with the new theoretical and modeling capabilities that are available on new computers, you can actually shine the light where your experiment needs to go. You don't have to go through trial and error. You can actually zero in on where you think the next structure you should synthesize should be. So it's very important to keep those together. So now I'm going to go through solar energy, and again, I won't go in a lot of detail. With solar light, you can make fuel, you can make hydrogen, you can make sugars, or you can make electricity, and these are the 3 sorts of sources that do that. You can mimic photosynthesis. You can use this type of cell that basically generates the backwards part of a fuel cell, just run it in reverse, and you get oxygen and hydrogen out instead of using hydrogen in here. And then the other one is to use photovoltaics to generate electricity. So those are 3 different areas of research. Photovoltaic devices have gotten better over the years, okay, especially with the advent of nanoscience. And I think this is areas that are just really exciting to see some of these nano scale materials approach where crystalline silicon is, and even beyond. This is an old slide. It kind of cuts off here in the late 90s. But I think there's a lot of advantages to going to these nano materials. And I know people here are working on photovoltaics and other sorts of solid-state lighting sources. And nanoscience is really revolutionizing our capabilities in this area. Where we have to be is we have to get sunlight and channel it without losses. So looking at materials with new tailored architectures, looking at materials that have a broad absorption over the entire solar range. Right now it's very hard to get things in the infrared and areas like that to take advantage of all the different wavelengths that are in the solar cell. And then looking at new processes for making these materials in thin layers and defect-free interfaces and catalytic pathways. This is kind of the bottom line. You'd like to take something that would have some way of harvesting the light, get it to excite a system so that it had charge separation, and then use the catalyst then to affect either production of fuel or production of hydrogen that way. And so a lot of interesting work being done in these extended porphyrins where you have these different metal centers. Very important to kind of get past the one electron problem, to get multiple electrons to affect these photovoltaics, just like nature uses in photosynthesis. So one of the things that, again, goes back to what I was talking about in hydrogen is no matter what we do, we have to store the energy. And I think everybody that I've talked to realizes that we think we can get the energy some way or another, but storing the energy is going to probably be the biggest bottleneck we have. And we all think about batteries, okay? And batteries is one way of doing this. Energy storage, even if we don't use it for storing large, massive amounts of energy to level out solar, again, I would venture to say that you guys know a lot more than I do, especially in the electrical engineering areas, is that our power lines are very noisy. I rarely go home during the week without at least having 1 day or 2 days where my lights have spiked and you know, throw my microwave timer off, right? And this is critical for industry, for the power, for the semiconductor industry. If they have a spike like that, they ruin their chips, okay? So they go to great lengths of putting storage devices in line with their power to try to smooth out these excursions. And the more and more we get on the grid, the more and more excursions we're going to have. And so this is something that's of high interest to the power companies. But it's primarily what I'm going to be talking about is using these for cyclical energy sources. Plug-in electric and all-electric vehicles put even greater demands on storage, okay? So it would be wonderful. I mean, I don't know how many of you guys have a hybrid automobile, but they're wonderful, okay? So my daughter's got a hybrid car, and it makes many, many gallons per mile. And it's really wonderful, but the idea is could you go to a full electric car? Okay, taking advantage of plug it in at night when energy use is down and then run it the next day. The problem is that today's batteries don't last very long, okay? So you can't go very far if you were going to plug in electric. And most of us drive more than 40 miles a day, which is about what a typical plug-in can do right now. This is the Tesla down here, and this car has 4,000 batteries in it. 4,000, I think it's 4,000, okay? Somewhere in that neighborhood, 4,000 lithium-ion batteries. It goes, okay, but it's not a practical car yet, unless you're Arnold Schwarzenegger who bought one. Anyways, has one on order. But this is something that is extremely appealing, and it's a great way to store energy that's made during the day. You plug it in, and then you go. But these batteries have to have more energy. It has to discharge it faster. It has to be charged fast, because you don't want to wait 8 hours to recharge your car. You want 5 minutes to charge your car, right? You don't want to stand and wait if your car runs out of juice. So there's a lot of needs for electrical energy storage. So again, I think you probably all know how a battery works, but I like this quote. You know, batteries were invented 200 years ago, and they really haven't changed much. They're 2 electrodes, they're an electrolyte, you charge them, they discharge, and they look very simple, okay? We use them every day, but actually they're one of the most complex chemical and physical systems you can think of, because batteries are not just 2 solid electrodes with an electrolyte in there. These are graphite electrodes. This is a lithium battery, and you're actually putting ions, lithium ions, into that electrode and pulling them back out every time you charge and discharge that battery. So when you do that the first time, that battery never looks the same as far as looking at those electrodes. It's different every time you go through these cycles, and that's why they fail. So you may have a Dell battery right now that lasts for 5 years. But you go get another battery, it might last for 5 days. And it's because of this irreproducible chemistry and physical properties in these electrodes. And this is a real limitation of batteries. And this is what happens to safety and long lifetimes. And you have to go through all these discharge, and you have to get more energy per unit volume. You don't want the back half of your car to be lithium batteries, okay, which is what the Tesla is. So this goes to show you what I was talking about, where these ions come out and you start getting, it looks like cavities. Everybody says that looks like a cavity picture, but it's actually where this stuff is just coming out of these materials. So you get these erosions, and you can get stalactites and stuff coming off that actually short these batteries. So there's a lot of problems there. So the idea is to come up with tailored architectures, self-repairing, come up with new electrolytes that go beyond 4 volts, because we're running these batteries really at the limit of thermodynamic stability. And then design electrodes and electrolytes as a system, okay? So you can get rid of this problems about the interface, this SEI interface that you have, where you get this irreproducible physical changes. And be able to look at these, again, the same theme of in situ characterization tools and computational models. This is another device. I'm not going to talk about it, but this is a capacitor. And these capacitors are used in hybrid vehicles now, that when you step on the brake, you charge a capacitor and it trickles it down to a battery. This is in every photocopying machine. This allows you to have photocopy machines that discharge quickly. This thing will hold a lot of energy. It'll discharge really quickly, but it has no power. Okay, it has good power density, but it doesn't have sustained energy. Okay, so these are something that people are looking at, and they're already in use. They use them in these elevators that raise loads over to ships, and when they raise it, it uses energy. When it lowers it, it releases energy and stores it. They're actually making these capacitors to go in soldiers' boots, so that when they walk, that when the shoe flexes, it actually stores energy and runs all that equipment on their uniform. And again, these are things that are used this is a semiconductor, outside a semiconductor plant in Japan. They're actually, capacitors are used in buses, although this bus can only run for 15 minutes. It goes around the square once and they have to recharge it. It charges very quickly though. It charges immediately because it does not require the physical interplay of those ions. It only stores charge, so it does not intercalate into the electrode battery. So capacitors are interesting. So again, these are the areas. I won't go through those because I need to move on, but electrolytes and so forth. And this was a cool thing about a 3-dimensional battery, instead of having just 2 electrodes and electrolyte, is to make this nanostructure. This is work that's going on at the Naval Research Laboratory. It shows a lot of promise. This is work of Deborah Rawlinson and her colleagues. And this is the final thing, materials under extremes. No matter what we're talking about, materials are always the limiting properties of these energy technologies. I've mentioned materials that can work under higher temperature, under higher pressure, being able to charge things to higher voltages, these sorts of things. In all of these different applications, we need better materials, and that's not going to be accomplished unless we do basic research to try to come up with ways to get around defects, the inherent defects. Can we use those defects to our advantage? Can we get some way that these defects will self-repair or self-report so that we know when a bridge is going to fail? So there's all sorts of interesting things. This is the last report that was brought out, and this is very interesting reading because it kind of cuts across all of the different energy reports that we had. So as a bottom line, we have all sorts of extremes that we have to make materials work under. We have to have turbines that work for longer periods of time, photovoltaics that work for many years on top of your roof. You're not going to spend that kind of money to have to change it out every few years. You want your roof, these solar cells, to last for 30 years or 50 years or whatever. And this is an interesting thing for those who do nuclear engineering. This is a control stainless steel. Okay, this is a 316 stainless. This one is the same material that was exposed to neutron flux, and you can see there's huge changes in the dimensions of a stainless steel just due to impact with neutrons. And so these are the types of things that people are working on to come up with more stable materials that can last for a long time, so you don't have to shut down reactors and redo all of the containment process. And so there's a lot of really nice science to be had here. And if we understood, we don't even understand why neutron impinging on that steel causes this, okay? We have to understand why that happens before we can even devise ways to do that. The other thing is can we use these extremes to make better materials? Can we use neutrons to make a harder material, for example? So if we understood how it worked, we might be able to harness it to make improved materials. So this is kind of the end, and I'll open up for questions. This was the Crosscutting Science for research that came up, and you can kind of read through here. The whole idea is that we can make materials, we can design them with the functionality that we want and that we need for advanced energy technologies, but it's going to require a close coupling of the synthesis up here with new tools to look at spatial characterization and time resolution of the reactions that happen. Okay, we have to be able to look at things dynamically. Being able to use multi-modes of observing reactions and physical properties, so you might have infrared, you might have electronic behavior, you might want to look at voltages and things like that. Temporal studies, and then theory and computation. And so these were the conclusions. There's enormous gaps right now between present state-of-the-art capabilities and the requirements for the future, and that we're not going to just get to where we need to be by simple improvements, and that technical barriers can only be overcome with high-risk, high-payoff basic research. And the fact is that we have to have interdisciplinary research, and this research between the coupling of applied and basic research should go together hands in hand to make that advance. And I'll just say one thing. Those of you who are students, I think this is probably one of the most interesting times to be involved in science and engineering. There are huge challenges out there right now. I mean, just incredible challenges that you as students are going to have the opportunity to solve. And I think that for the next 25, 30 years, a whole career, and maybe more, this is the type of science that this country needs to have, and needs to have well-trained students like yourselves to tackle. So I hope you have a good time doing it, as I and others in this audience are kind of looking at the back door of our careers. I'm hoping that you guys can come up with good solutions to this issue, because it's going to impact the whole world. And I think it's that important that we pay attention to it. Be glad to answer any questions. Yes? Yes.
And I stand with you correctly, but my understanding is the highest theoretical efficiency right now, and this is for cadmium telluride at thin film, is 27%.
Right.
Okay. And of course, thin films are much easier, much cheaper to manufacture, and they can be done here in this country. But in line with that, you mentioned that you were kind of fearful that we're so behind, and one of the issues is that we don't do crystals here. We only have one bulk crystal company in the United States, and the reason we don't do them is because we cannot compete with our foreign competitors. And one of the reasons we cannot compete is because, for example, Japan, the government subsidizes their companies. So my question then is there any effort in order for us to become more energy independent, because transportation uses energy, right? Right. That the government can help in that area as far as bulk crystals.
Well, boy, you've asked a political question, and I'm just a poor old scientist. But the answer is yes. I mean, I think that the synthesis of materials has been identified as a critical need for all of this, okay? And bulk crystals is very important, as well as making thin films. Now the question is what can we do to kind of boost that kind of production in this country? And I think that what we're talking about is that just this is coming up with new ways of doing this that makes it more economical, makes it more reproducible. I mean, it's hard to grow single crystals. Okay, it's very hard as a technology. We've got a group in Oak Ridge that does that. But there's few places in the country that does it even for research, let alone in production levels. So I think that if we could come up with better ways of doing it, okay, through research, that would help. I can't answer whether the government should subsidize like the Japanese and Europeans do. That's a whole other level of arguments as to what we subsidize in this country and not. But I think we're going to get to a place where the government's going to have to act either by doing research or helping industry get us to where we need. You know, I think we're getting to a crisis point in this country that we have to do something, okay?
I have one more question, and that's about our biofuels and in particular ethanol, and that would be corn ethanol. I don't have a particular problem with the cellulosic ethanols and methanol, but corn ethanol, and I guess all of the fuels that we are deriving from biomass, how much is looked at by the fact that in removing biomass, you're removing some of your carbon dioxide sink, okay? And also ethanol, in particular corn ethanol, is very, very expensive. It uses a lot of energy to produce it.
Right.
And it's got a very, very low efficiency.
Right.
And probably the majority of the cars in this country can't take a high amount of it because it's corrosive.
Right.
So that's what I was wondering about, you know, that corn ethanol, whereas the other types of ethanol, methanol, and cellulosic ethanol, I think are.
Well, my feeling is that bioethanol is something that's going to shore up the gap between now and the time we come up with non-carbon-based materials. And I think if I had to look in my crystal ball, that's what I would say, okay? I think that corn ethanol and cellulosic ethanol have uses, but I would much rather see, personally, those carbons going into feedstocks, for chemical feedstocks, and for us to go to a non-carbon-based area. I think you brought up some really good points, though, because people don't talk about the fact that the certification company, it's not ASTM, but it's another certification company that certifies our gasoline pumps, won't certify an ethanol pump because they can't keep it going because of the materials problems, the metals and the gaskets and all this kind of stuff. There's huge problems with materials compatibility. You can't pipe it, so they're going to have to truck it. So, you know, when you look at this from cradle to grave, there's a lot of issues with bioethanol. Are they insurmountable? I don't know. I'm not an expert in that area. But you've brought up some really good points that I think people in the community are looking at. Because, again, I don't think there's any one good solution. And so it pays to look at different endpoints. Yeah.
So the motivating factor be energy independence or to drive and reduce the carbon footprint? Because you started off the top talking about global warming and biomass. People have found actually the carbon footprint is greater than for the energy it produces. Right. And just a comment about the ethanol fuel. I mean, I guess there are more energy efficient ways of producing ethanol. Like the Brazilians have done a pretty good job with sugarcane ethanol. Right. You have ethanol pumps everywhere.
I think the answer to your question about whether it's reducing CO2 or becoming energy independent, the answer is yes. Okay, it has to be. It has to be. We can't be dependent on going outside our shores to get energy and for us to be hogs about the energy and then say to these other countries, oh, we want a quarter of the world's energy supply. Okay, that ain't going to work very long or we're going to have real problems, okay? So we have to come up with a way that we can produce our own energy. I think every country is going to have to do that. So how do we do that is one of the questions. And I think that eventually we're going to have to get rid of that carbon dioxide. I mean, we can stick it down holes. We can do different things. Maybe we can catalyze it to methanol or something like that. But eventually we're going to have to come up with some way that's clean. Okay, so sequestration with ethanol or going to a non-carbon-based system is, I think, what we're looking at. Yes?
One of the topics was advanced nuclear.
Yes.
Can you give us an idea of what are they talking about, fusion still? Or?
Well, yeah, fusion is still 35 years away, the typical thing. You know, fission is something that we just have not invested in this country for 25 years, right? And so a little more than 25 years. And it's still a hot button, but I think people are rethinking this. I think it is a viable option if done correctly, and I think we've shown that we can do it correctly. you know, going away from the public opinion of nuclear, it's a very good technology, but if you look at that, even that isn't going to be enough. Okay, you have to build Rick Small used to say this, a gigawatt plant every day for the next X years to meet the needs of this country. So we're not going to be building them that quickly, but we have to come up with better designs that don't have the problems with proliferation that we have now. Okay, so you look at some of these little encapsulated fuel type materials, looking at closing the fuel cycle, those sorts of things. There's a lot of advances that have to be made to make nuclear beyond what we have now, to make it more effective. And of course, in the end, we also don't have enough uranium, okay, to last forever either. So you have to start thinking about fusion or other things to make a nuclear cycle. Fusion, I'm not gonna comment on, because that's still down the road. Okay. Yes.
How much focus has there been on medium term and solutions that will give us enough time to come up with these breakthroughs?
I'm glad you asked that question, because I think it's really important that we all realize that we can't wait, okay, 50 years to come up with, you know, technologies that'll work then. We have to have a balanced research portfolio between near-term applied research and longer-term basic research. And so it's important that we realize that, because we can get places very quickly in our applied areas. But I do think that eventually that synergy between the applied and the basic is what we're going to do to get to the 50-year or 100-year window that we need.
Please join us for a reception in the atrium. And